Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I changed the title of my talk to Pushing the Bounds of Subtyping, because this is the first part of the talk I originally thought to give. Some of this is based on joint work with Julien Crétin and Gabriel Scherer. The dawn of subtyping, I think, is in the 60s, although it's so natural concept that it should have been ideas before. But the first formalization of subtyping is in 80 by John Reynolds. And then in 84, Luca Cardelli came with his language Humber that had a lot of amazing features. So it looked very complicated. However, I think it was very simple, especially if we look if we compare to what kind of languages we're trying to develop today. The reason why it was kind of easy is because type system was based on simply type on the calculus and subtyping. So there is this subtyping rule that if a program has type tau, and then tau is a subtype of tau prime, then A has type tau prime. Subtyping is a binary relation, and in a simply dynamic calculus, it's very simple. It's built from axioms that brings into the subtyping relation some facts. In a real language, you would have something like int is a subtype of float, and then some structural rules to propagate the subtyping relation through type constructors. This is the well-known contravariant rule for arrow types that says that two arrow types are in relation if the codomains are in the subtyping relation and the domain are in the inverse relation. I'm skipping a lot, an essential part of the story, of course, because Humber had many other features, especially records, subtyping on records, concatenation on records, that played a key role for the semantics, the encodings of objects and multiple inheritance. But this is not the point I want to make there. In fact, Humber had many more features. It also had recursive types, modules, dynamic types, concurrency primitive. What I find really amazing is that, in a way, Luca had a vision, because at that time he already put in the language things that were going to keep our community very busy for the next decade. And he himself contributed to explore each of these topics in depth. At the same time, we had polymorphism, and Luca also did some work on polymorphism earlier because he, for instance, worked on ML. The question then is, how do you mix polymorphism with subtyping? In system F, you just have for alpha sigma as a polymorphic type. And the clever idea of Cardelli and Nögner is to say if we want to mix them, it actually suffices to add a bond, which is bonding quantification, to polymorphic types. So this stands for the set of type sigma, where alpha ranges over subtype of tau. Bonded polymorphism allowed to not have subtyping as facts, as we could do before, but now to have reasoning under hypotheses. Now we can say that sigma is a subtype of tau under some assumptions on alpha. And once you have that, you can also have subtyping between polymorphic types, which is a famous rule for F sub that Benjamin mentioned, and there were many variations on the rules that I don't want to really comment on. Bonding quantification is very expressive, and it has been the base of many works in the 90s. And I think every type system that had subtyping in polymorphism was to do something around F sub. Still, despite it's very expensive, it still lacks a few things. For instance, it only allows a single upper bound. Why should it be so? Because subtyping, a priori, is a symmetric relation. And also, subtyping doesn't allow type instantiation of quantifiers. Well, this is not by mistake of design, of course, but a design choice. The choice was to make subtyping decidable according to the right variant of the rule you choose, and tractable. And by keeping quantifiers explicit, so that subtyping could be implicit. So this is a good balance point in system F sub. Still, you could consider type instantiation as part of the subtyping relation, and indeed this is what ML does. the only thing that ML does is to say that a polymorphic type is a subtype of all of its instances. This same rule was reused by John Mitchell in type containment when he was using that rule and then added the amber rules to propagate subtyping through arrow types. So that then you could instantiate not only at the top, at the surface of a type, but also deep inside term by going contravariantly on arrow types. However, type containment doesn't subsume bounding quantification because it doesn't allow it to reason under hypothesis. Yet another form of quantification is instant bounding quantification that I introduced myself in to do partial type inference in system F. Here we write types of the form for alpha that is an instance of tau, sigma, which stands for the sets of type sigma, where alpha ranges over instances of tau. And this constructions was a key to avoid having to decide too early whether type should be instantiated or kept polymorphic. I don't want to go more into the details of MLF, but what appears here is that we have new flavors of new forms of typing, and the natural question is, can we combine them together? So a question that I wondered was whether we can combine MLF subtyping or whether F sub and type containment could live together. Yet another question we may ask, if we take all features together but restrict the subtyping relation in other ways, for instance, to restrict subtyping to a relation that would be invertible, as is the case in the internal language of Haskell. And in fact, we would like to do more, because if we want to encode subtyping constraints that naturally appear when you want to extend ML with subtyping, then we would need multiple bonds. Also, we'd like to have recursive types in the most general form, which implies co-induction. Besides, I would like to do this in a setting that have full reduction. Why do I want to do so? Because it should work with full reduction. And if I'm not able to prove that it works, it means that there is something that I haven't completely understood about subtyping. But also, full reduction models the reduction of open terms, and it avoids postponing type errors under type instantiation, under type abstractions. Moreover, if I can do it for full reduction, then I would get the result for a weak, any form of full reduction, so I won't have to redo the proof for ML or Haskell. I'll do them once for all. Another thing is, in fact, I argue that I think full reduction is a better model for a programmer. It's a more abstract model, and it should be enough to think about functionality. The weak reduction model is only necessary when the user wants to reason about the cost of computation. So to do so, we just modify bounding quantification, and now we introduce quantification for alpha, such that P, where P is a proposition that could be a conjunction of subtyping constraints, so having multiple subtyping constraints. This is the way we'd like to understand it, but technically it's more convenient to treat it as a bounding quantification with kinds. So I want to introduce for alpha of the kind K, where K is a kind of power is a kind of form of power kinds that Cardelli introduced in '88. So I will have these kind that represents the sets of types alpha that satisfy the property P. Then there is a problem that comes that appears. Now that we have multiple bonds, we have to be careful that our kinds are inhabited. Otherwise, we could just hide type errors under inconsistencies in kinds. So here is an example. We could type 1 apply to true with give it type int by assuming that it's polymorphic over some variable alpha of this inconsistent kind that assumes that int is below bool row int. And we could build, if we didn't care, if we didn't check about consistency of kinds, we could do a derivation when this inconsistency goes from hypothesis into on the right-hand side, and we'll be able to type that. So terms with incoherent constraints, they cannot be safely reduced. This is easy to implement. When we build kinds, when we build polymorphic types, we have just to be careful that the kinds are inhabited. So we had a premise when we provide a witness sigma for the kind. However, we also want incoherent. We also want to deal with incoherent kinds, because there are situations where a kind won't be coherent for all instances of the context, but only for some of them. And this is a typical situation when you type check GADTs. So we introduce yet another form of quantification, which is the inconsistent polymorphic abstraction, when the kind here may be inconsistent. As a counterpart now, because we cannot reduce, if we assign a term such a kind, we cannot reduce under it, so we need to introduce a new construct to freeze the abstraction when we introduce such a kind, and then another construct to unfreeze it when we instantiate the kind. So to conclude our short journey, what we have is an external language for exploring the design space. We've put all the features together. This is very expressive, and it is sound. However, we lost subject reduction. First, this language is not quite suitable neither for a surface language nor for an internal language. For a surface language, because we put everything in, if we wanted the explicit version of a surface language, this would be it verbal, so it's not exactly what the user would like to write. For internal language, because we don't have subject reduction, it's not quite suitable. This is, in a way, a limitation, but on the other hand, I think it's a good point to have explored this in an external language, because now we have shared the meta theory and separated the study of meta theory, what we can do, from the design of the language we want to use. So now that we know the bond of everything we can do, we can play with sub-languages that could be used as a surface or internal language. Subtyping has played a very important role in Luca's early works, and I think Luca contributed a lot to make subtyping well understood, but still there are a few variants of subtyping and uses still to be explored. So I would like to thank you, Luca, for all your inspiring works and a profusion of new ideas that kept us moving forward faster and further. Happy birthday.